The figure you see here depicts a loop between the poles of a magnet, north and south poles of a magnet, that's what these things indicate. And this loop is rotating in this magnetic field, and as you know, that's going to change the magnetic flux and produce a potential difference between the points A and B. A being at one end of the wire, and we go around here and we get B at the other. The potential difference between A and B is going to be delta phi over delta t, change in flux over change in time, or if we take the limit, the calculus definition is d phi over dt. The flux is just B times A times the cosine of theta, where theta is the angle between the magnetic field and a normal to the loop. So as the loop rotates around, the angle between its normal vector and the magnetic field continuously changes. Then, if the angle is given by theta equals omega t, in other words, if we have the loop rotating at some angular frequency omega, then the angle will be theta equals, could be represented as theta equals omega t. The flux will be B times A cosine theta, which is B times A cosine of omega t. And the voltage is just the derivative of the flux. Now here's where students who don't have the calculus background aren't going to understand what's going on, but you can understand the result. The derivative of this function is easily found to be negative omega B A sine of omega t. And the details of how you get that are based on calculus, but the result is simply that we get a current that alternates as the sine of omega t and has a maximum amplitude, not a current but a voltage that alternates as a sine of omega t, and has a maximum amplitude of negative omega times B times A. Now the units of negative omega times B times A, and what's wrong with the focus here? The units of negative B, of omega BA are Tesla times meter squared times cycles per second, and that's just volts. So negative omega BA, or omega BA, is the maximum number of volts that you're going to get in this alternating current, and omega is the angular frequency of that current. And I keep saying current when I mean voltage. We get voltage versus time, we get something like this. Now when you look at the voltage that's produced by your handheld generator, it looks something like this. The time scale here is different than the time scale here, and I really should have kept it the same, but this is really what you see. It's just a compressed version of this, but we've got diodes in a circuit that essentially inverts the current, and when the current is high, when it's positive, it gives us a positive current. When it's negative, it inverts it, still gives us a positive current, and it gives us this current that really doesn't change much. It's almost a straight line current, but there is some fluctuation. That's what happens, and we're not going to go into the details of how that's constructed, but that's what happens with the handheld generator, so that we essentially take this alternating current that we get from the rotating loop and turn it into almost a direct current, almost a constant voltage. I'm saying current again. We get an alternating voltage, which will of course give us an alternating current, but it changes that alternating voltage into constant voltage, or near constant voltage. So what we have when we crank the generator on a circuit is the loop in the magnetic field between the two poles of a magnet and an inverter of some kind, and that feeds out into the circuit a more or less constant voltage, or that creates a more or less constant voltage between this point and this point, or between A and B. So that we can depict what happens as a constant source through a resistance, let's say. We could also have capacitors and more complex circuits, but this is what's going on with the generator.